Chapter 6, Covalent Bonding. Chapter 6, Section 1, Covalent Bonds. In this section, we're going to look at the formation of covalent bonds, and we're going to talk about the degree of ionic character within covalent bonds. A covalent bond is defined as a sharing of electron pairs between atoms. So this is different from ionic bonds, where in an ionic bond you have a transfer of electrons, where a metal gives up its electrons to a nonmetal. In covalent bonding, we have two nonmetals that share electron pairs. So for example, here we have atom C and atom D, and they share a pair of electrons. This makes a molecule. Again, different from an ionic bond where you form a crystalline lattice.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms. The first energy level in atoms can hold 2 electrons. By sharing electrons in a covalent bond, each hydrogen atom has a full outermost energy level. Water molecules are also held together with covalent bonds. Again, we see that covalent bonding gives each atom a full outermost energy level. The outermost energy level for hydrogen can hold 2 electrons. The outermost energy level for the oxygen can hold 8 electrons. In covalent bonds, the shared electrons move between the atoms that share them, forming a single electron cloud around both atoms.
Energy and stability. So we know that most elements on the periodic table do not have a complete octet or a complete valence shell. These elements then have a low stability. In other words, they want to form bonds in order to achieve that complete octet. For example, if we talk about the element hydrogen, hydrogen is a group 1 element, so it has only one valence electron. If hydrogen can obtain one more valence electron, it would become a noble gas configuration as helium. So hydrogen typically bonds with other hydrogen atoms to achieve that complete octet. When they have complete octets, they then become more stable. Bond length is defined as the distance between two bonded atoms at their minimum potential energy. So we are going to look at figure 4 on page 192 of your textbook and look at the bonding of two hydrogen atoms. So the two blue spheres here on the graph represent two individual hydrogen atoms. Other things to note about the graph is that potential energy, which is the energy of position, is along the y-axis, and the distance between the hydrogen nuclei is graphed along the x-axis, and notice it has units of picometers. So we're going to talk about the 3 main points along the graph. So at point A, we have simply just 2 hydrogen atoms that meet as separate atoms, and there is no forces between them. As we move from A to B along the graph, at point B, the attractive forces pull the atom together. In other words, the nuclei of one atom is attracted to the electrons, the valence electrons of another atom. And you can see that the potential energy values are starting to decrease. As we move from point B to point C, this is the lowest potential energy point along the graph. This is where a bond has formed. So the lowest point on the graph corresponds to bond energy. Bond energy is defined as the energy required to break a bond between two atoms. So in other words, what this means is that we're putting energy in to break bonds, and then when atoms bond together, they release energy. So there is a direct relationship between bonds and bond length. And the relationship is the shorter the bond length, the stronger the bonds. And then this is verified for us in your textbook in Table 1 of page 193. And you may also want to notice that the very first one listed there is the bond between hydrogen and fluorine. And remember that fluorine is the most electronegative element on the periodic table. In other words, it has a great attraction for electrons. Electronegativity is important when we talk about covalent bonds and ionic bonds because it allows us to predict bond type. So just as a review, a covalent bond forms between two nonmetals. Remember that there is a stair-step line on the periodic table and that the elements to the right of that line are known as nonmetals, and elements to the left of that line are known as metals. And then what differentiates an ionic bond is it's a bond between typically a nonmetal and a metal. And ionic bond forms this because you have a transfer of electrons. The metal gives away its electrons to the nonmetal. Electronegativity can also be used to determine the type of polar or covalent bonds. And covalent bonds can be nonpolar, and what this means is that there are two atoms bonded together, and those two atoms have very similar electronegativity values. In other words, they equally share the electrons. So a great example of this is two atoms that are bonded together that are exactly the same. So in the picture, the molecule on the left is two fluorine atoms bonded together. So those two fluorine atoms would have the same electronegativity. They would have the same attraction for that pair of electrons. The molecule on the right is two hydrogen atoms bonded together. And again, they would have the same electronegativity. They would have the same attraction for that pair of electrons. The other type of covalent bond you can have is called a polar covalent bond. And in a polar covalent bond, you have two atoms that do not have the same attraction for the pair of electrons. So there is an unequal sharing of electrons. In other words, one atom is going to pull the electrons closer to it than the other. A great example of this is in the picture. There are two molecules of HF, and you can see that that pair of electrons being shared is closer to the fluorine nuclei than the hydrogen nuclei. Now, the other importance about who gets this pair of electrons is that unequal sharing creates what we call a dipole. So a dipole is when you have a molecule or part of a molecule that contains both positively and negatively charged regions. Now, the way that we obtain these regions is as follows. The element that is more electronegative pulls the electrons toward it, which gives it a negatively charged region. The other element has its electrons pulled away from it, which gives it a positively charged region. So again, let's use HF as our example. And we should recall from chapter 4 that fluorine is the most electronegative element on the periodic table. So fluorine would pull the electrons toward it, which would give it a negative region, and hydrogen has its electrons pulled away from it, which is going to give it a positively charged region. So the symbols that we see here are the symbols we use to differentiate for these regions, because we're not forming ions. These are regions of positively and negatively charged. Okay. So the symbol kind of looks like an 8. It is the lowercase delta. It means the partial. So if you see the lowercase delta followed by the positive, it means that that region of the molecule has a partial positive charge. If you see the lowercase delta followed by the negative, it's to show that that region of the molecule has a partial negative charge. So we've talked about the relationship between bond length and the strength of a bond. We can also talk about electronegativity difference and the strength of a bond. So the greater the electronegativity difference, the greater the polarity, and the stronger the bond. So in the diagram, there are 4 molecules, all containing hydrogen and a different halogen. So again, remember that fluorine is the most electronegative element on the periodic table. So HF is going to have the greatest electronegativity difference, and notice it has the highest bond energy. Also, please remember that electronegativity difference is always positive. So in this case, in how they derived the 1.8 is they took the electronegativity value of fluorine minus the electronegativity value of hydrogen. So 4 minus 2.2 is 1.8. Okay, we have one more bond to talk about, and that is the metallic bond. So a metallic bond is when you have a piece of metal, so aluminum foil, copper piping, so it's all made of the same type of atom. So remember that we're looking at the metals. The metals are on the left side of the periodic table. Previous knowledge that we should have about metals. So metals, okay, because they're on the left side of the periodic table, they do not have complete p sublevels, and in some cases they have empty d sublevels. So for example, sodium doesn't have any electrons in D. In metallic bonding, because they're vacant, these orbitals overlap. And so electrons move then throughout the metal. And what this means is that these electrons do not belong to just one atom. And this creates what we call a SEA of electrons. And metallic bonds also create a crystal lattice.
The outer electrons in metals are able to move a lot more freely than electrons in nonmetals and metalloids. Partially empty energy levels offer multiple positions for any given electron. Since outer energy levels of adjacent atoms are relatively close together, electrons in metals can also move from one atom to another. The result is metallic bonding. The positive metal ions remain in relatively fixed positions, while the negative electrons are free to move about. This creates bonds extending through the metal in all directions and leads to many of the observed properties of metals.
Okay, so we spent time in chapter 4 talking about the properties of metals, and this gives us an opportunity to talk about why these properties exist. Okay. So remember that one of the properties of metals is that they have luster. In other words, they're shiny in appearance. The reasons for this is that their orbitals that are empty are close together in energy. We know that they can absorb frequencies of light. We know that whenever that happens, it moves the electrons to an excited state, and that state is unstable, so they drop back down to the ground state. And that light that's given off when that happens, okay, or reflected when that happens, is why it appears shiny.
Metals can absorb a wide range of light frequencies because they contain many orbitals separated by very small energy differences. Electrons readily absorb photons and jump to higher orbitals. They then almost immediately fall back to their original levels, emitting photons. This is what gives metals their shiny, reflective surface.
The other properties we've talked about of metals is that they have high electrical and thermal conductivity. Remember that in order for something to be conductive, you have to have charged particles that can move. In this case, the fact that those electrons are moving around because they don't belong to one atom creates that. Metals are malleable, so they have the ability to be hammered into thin sheets. So the fact that we have the C electrons allows atoms to slide past one another. And this is the same reason why metals are ductile. In other words, they can be drawn into wire.
The malleability and ductility of metals are possible because metallic bonding is the same in all directions throughout the solid. When a piece of metal is hammered, one plane of atoms in a metal can slide past another without encountering any resistance or breaking any bonds. When a piece of metal is drawn or squeezed, the atoms slide past each other without breaking bonds. This ability of metals to be shaped by hammering or drawing is the basis for much of the technology that we use in our daily lives.
Okay, so let's summarize our three types of bonds. In metallic bonds, we have a piece that's made up of only one type of atom, and that atom has to be a metal. You can see that they have fairly high melting and boiling points. And again, because they have this sea of electrons, they are good conductors. Because they have high melting and boiling points, we would expect them to be solids at room temperature. And then potassium is a group 1 element, and we know that group 1 elements tend to be soft, so they can be sliced with a knife, and they're silvery in appearance. Ionic bonds are made up of a metal, nonmetal, so potassium's a metal, chloride is the nonmetal. These have extremely high melting and boiling points. This tells us that it has a strong bond, so we would expect these to also be solids at room temperature. Ionic compounds have the ability to be conductors as long as they're melted, because that's how we're going to get charged particles that can move, or they've been dissolved in water, and again, that's how we're going to get charged particles that can move. And the last type of bond is covalent. Covalent has to be two nonmetals bonded together. So in chlorine's case, it's two chlorine atoms bonded together. These have very low melting and boiling points. So typically covalent compounds are gases or liquids at room temperature, and they do not have any charged particles, so they are not a conductor. Alright, so here is our models. We have metallic, which has a sea of electrons moving around because they don't belong to just one type of atom. Molecular covalent, you have two atoms that are sharing a pair of electrons. And in ionic, you have a crystalline lattice. And in that crystalline lattice, you have metals that are giving away their electrons to nonmetals.